Head of the department, madam.
Where is my face?
Yeah, here you go.
Sir.
So, Professor Seema Pathak.
Sir, thank you so much. And I wanted to meet you in person because you supported us a lot on certain points. And this just training Dr. Anirban Das in such a good manner, and he's actually gem of our department. He's working so hard and so positive person. Thank you, sir.
Thank you.
So anytime, please do come physically.
Sure. Sure, I will come, sir.
Thank you, sir.
Thank you, ma'am. So we have Professor Ram Sagar for this session chair. So I would like to invite Professor Ram Sagar to introduce Professor Ganguly. Sir, please.
So, hello, good afternoon, Professor Ganguly. So, it's my great honor to chair this session. And Professor Ganguly is currently serving as a director at ISAR Berhampur. And he is superannuated from IIT Delhi, recently continuing as an honorary professor of chemistry. And he's also honorary professor at JNCSR Bangalore. And he was earlier Deputy Director of IIT Delhi during 2019 and 2022, and was also the founding director of Institute of Nanoscience and Technology, Mohali, India, from 2013 to 2018. His main research interests are in the area of design of nanomaterial for energy applications and bioimaging, and also in superconducting material. He has published over more than 450 papers and has filed 6 patents and 3 has been granted. And he is a recipient of many medals, including MRSI medal, CRSI silver medal, CRSI Sina Rao, National Prize, National Awards of Nanoscience, Nanotechnology from DST, and many more awards are in his credit. And his Lifetime Achievements Awards of Indian Chemical Society and gold medal from the Society of Materials of Chemistry. And most recently, he was awarded a Lifetime Awards of IIT Delhi. And he is a fellow of all 3 science academies of India, INSA and ISC and NASI, and the Royal Society of Chemistry, London, and the Asia Pacific Association of Materials. Dr. Ganguly was a coordinator of Delhi SNMPT cluster, DRIAV Drive, and was also the part of the knowledge cluster of Chandigarh CRI-KC. And Dr. Ganguly has very keen interest to promote outreach activities of schools and colleges, especially in rural areas, and more than 400 schools and colleges he has visited in last 10 years. So he is one of the most outstanding material chemists in this country, and this is my pleasure. I am very much fortunate to read his brief biography, and I still remember I met him in Jawaharlal Nehru University when we organized the CRSI conference in 2023, and that time I get an opportunity to interact him in person as well. And thank you very much to all of you. And now this is floor for you, Dr. Kamal.
Thank you, Dr. Ram Sagar. Thank you for your kind introduction. I am very happy that Amity University, Manesar, is doing this meeting on material sustainability. I think is the theme. And I am very happy that you have, I can be part of this meeting, not physically, but at least I can connect online. I'm sorry that there was some glitch and it took us some time to figure out how to get online. And I thank all of you for waiting patiently. And I am sorry for the whatever glitches it is. So I believe I have half an hour and I'll try to give some aspects of my recent research in nanomaterials, which we have designed for photoelectrochemical cells, and also some aspects in which nanoparticles are being used in biomedical science. So shall I share my slides now? It's okay.
Yes, sir, you can share your slides.
Yeah, so if the slides are visible.
Yes, sir, it is visible.
Okay, so this talk I just gave in BITS Pilani, and I've reduced the talk because that was a plenary lecture and I had 1 hour or 55 minutes. So I removed some slides and I'll talk on some aspects of energy conversion. So I have several students and the work I'm going to talk to you is mostly the work recently earlier done by uh, Sandeep Kumar and Shalini, Preeti, Nitika, etc. on photoelectrochemical cells. And on the biomedical applications, I will speak about some work of Manisha. I may not have time to speak on the work of Manoj, but I'll try to see. I have collaborations with several faculty for ultrafast spectroscopy or biological work, which has been done by Professor Yu in Queensland, or Vivekanand Perumal at IIT Delhi, or Asif Khan in INST Mohali. They are my biology collaborators. And with Professor Paras Prasad, we have done work on scintillation and nano scintillators, which I will try to mention. The funds are mostly from I had two Vajra projects from ANRF, and the funds have been from that. So I moved from IIT Delhi to IISER Berhampur, and you can see it's on the coast. This is our new campus, and very close to that, we have the Bay of Bengal. These are several areas that I work on, if you can see. And I am going to talk to you today only on the right-hand side, the solar energy conversion, and maybe some aspects of up-converted nanoparticles for nanoscintillators. So this is what I said. I'll talk about photocatalytic, mostly photoelectrochemical properties, and some aspects of biomedical applications. And there are 3-4 examples. I'll try to cover at least 2 examples in biomedical applications. So all of you know that when we are looking for photoelectrochemical cells or even just photocatalysis, so we are looking for harnessing the solar energy and the solar photons. And when we are using nanoparticles, what is the role of the nanoparticles? The role of the nanoparticle here is to absorb the photons. So they are being used as semiconducting nanoparticles. And these photons, when they are absorbed by the semiconductor nanoparticles. This is a schematic picture. These nanoparticles create electrons and holes when light falls on them. And these electrons and holes are what is important for further uh, either producing electricity or doing some oxidation or reduction. So the semiconductor nanostructures or nanoparticles, they all help in absorbing the photons. And the choice of the semiconducting nanoparticle is how much photons can it absorb, how efficiently can it absorb the photons, and how efficiently it can manage the electrons and holes which are generated at the site. And all this then you can make thousands of different nanoparticles. You can combine 2 nanoparticles. So there are a lot of variety of architectures of the bands, because what are you playing with is the band gap of the nanoparticles and the conduction band age and the valence band age. So in this diagram, you see you have a host of materials which have band gap in the UV and visible are listed, and their conduction bandage and valence bandage. And why we use this diagram is here the water splitting levels are also given, right? So this conduction band of level and the valence band level of splitting water, that should be covered by these semiconductors. Okay, so that much energy which is required to split water is one of the features that many people have. Of course, not every time we split water, we can just work at one electrode and produce oxygen, or you work at the other electrode and produce hydrogen. So even that is the interest of many people. So oxygen evolution reaction or hydrogen evolution reaction are important, just as water splitting gives both oxygen and hydrogen at two electrodes. So this is the other basic slide, that the photons that you capture are having energies from the ultraviolet to the near IR, and all these photons are falling on the semiconductor, but the semiconductor nanoparticle has only a certain band gap and it can only capture some photons. So the other photons which are not captured leads to lower efficiency. So how can you design, say, a heterostructure of two semiconductors?
डिस्कनेक्ट हो गया भैया. Do you have his number? Call him to get reconnected.
Okay. अनिर्बान सर आप कॉल करें. आप कॉल करें.
Hello. Can you hear me?
Yes, sir. Now it is connected.
Okay.
It is.
Yeah, I'll share this. I may have to share the slide again. Oh,
Yeah, so they're visible now. Yes.
can you
Yes, sir. Yes, sir.
Okay.
Please.
So I'm telling you that engineering semiconductor heterostructures in the visible region is the prime activity that we had for a long time. So when you have these heterostructures, there are different aspects of these heterostructures which contribute to the efficiency. So one of the efficiency is the absorption of photons. The other is how much ease of separation is there between electrons and holes. And the third is how easily it is transferred to the electrodes, the anode or the cathode. The efficiency of each of these processes, if you multiply them, then you get the net efficiency. And depending on your system, whether you have an electrolyte or you have a solid, you have different kind of band diagrams you can draw. And there are some effects called band bending, etc., which lead to changes in the efficiency of the absorption of the photon and transfer of the electrons and holes as they are created in the lattice. So one of the first examples was taking a UV catalyst like zinc oxide and putting cadmium sulfide nanoparticles on top of that. This kind of geometry of two semiconductors is called a type 2 geometry, where the conduction band edge of one semiconductor is above the conduction band edge of the other semiconductor. The valence band edge of one semiconductor is above the valence band of the other semiconductor. So this we did long back. The paper was published in 2012, but it was quite well-cited paper, and we could show that with changes in the thickness of the second semiconductor on the top of the first one, we could change the band gap from UV to the visible region, and that enhanced the properties, which you can see here. You can see the photocurrent. The red ones have more shell thickness of the mid band gap semiconductor, which is cadmium sulfide. And the same property, which is enhanced photocurrent, can also be seen in the enhanced reducing ability of this material, which is zinc oxide with cadmium sulfide, 30 nanometer shell. And you can study the degradation of a dye, and you see that the degradation is much faster for this heterostructure compared to pure cadmium sulfide or zinc oxide. Okay, so this is one example where you had two semiconductors configured in such a manner that their band edges are in a certain energy level diagram. They are following a particular pattern in energy. Same thing you can reciprocate. You can change from zinc oxide to sodium niobate or cadmium sulfide to silver sulfide to indium sulfide. You can get similar properties. The numbers will change. For example, the effective band gap will change, so the effective absorption wavelength will change. The photocatalytic efficiencies will change. The photocurrent will change. But all of them show improvement because of the formation of the mid-band gap semiconductor as a shell on top of the UV photocatalyst, which is zinc oxide or sodium niobate. And this we could show in many materials. These are five materials. This is a sixth material, seventh material. This sodium niobate molybdenum sulfide. This is done more, that was done 10, 12 years back. This is more recent. And what is the change? The change is we are using non-toxic materials and more prevalent materials. For example, bismuth vanadate and molybdenum sulfide are more popular materials. And more recently, we have worked on these materials. The properties are the same. We can measure the current density, the photocurrent density, which I was showing like a plot. Here they are numbers, and you see the photocurrent density is increasing when we make the sodium niobate and molybdenum sulfide heterostructure. It goes from microamperes to milliamperes. So around 100-fold, 1,000-fold increase in the photocurrent. These are various measurements we do to find out about the charge transport. For example, the charge transfer resistance should go down. So the charge transfer resistance for the blue one goes down because that is a heterostructure of sodium niobate and molybdenum sulfide. Similarly, the charge transport of the green one is also lower compared to this cyan one, which is the bare sodium niobate. So lower the plots, lower is the transfer resistance. You can also measure other properties like the hydrogen evolution. You can measure, and you can show the hydrogen evolution as a function of time. You can measure what are called Mott-Schottky plots, and these plots give you from the shape of the plot, you can tell the nature of the charge carriers. So if you have a say positive slope, it indicates negative charge carriers, and a negative slope indicates positive charge carrier. So Mott-Schottky plot is a plot of 1 by capacitance square with the applied voltage. And you can see that here both the slopes are present, which tells you both types of charge carriers are there. That means in your heterostructure, you have one N-type and one P-type charge carriers, and that is reflected in your Mott-Schottky plots. Okay, so you have sodium niobate is one kind, right? And molybdenum sulfide is another kind. This is another method to explain that lifetime measurements tell you that how stable is your species. So if you have longer lifetimes, that means the species is more stable, and you can measure this fluorescence lifetimes. You can study the PL intensities. Smaller the PL intensity, it means the lifetime is more. That means they are not, electron and hole are not recombining to give you light. So photoluminescence should be low. And so for the blue plot, which is this sodium niobate molybdenum sulfide, is the best among all these materials in terms of the lower photoluminescence, which means longer lifetimes of electrons and holes. And that means the recombination is low. So various methods to prove that the lifetime is high, recombination is low, and that means you have more amount of time for the electrons and holes to reach the electrodes to carry out reduction or oxidation or produce current. This is a more recent paper. I just wanted to show you that these are more modern materials, more benign materials, bismuth, molybdate, calcium ferrite. These are popular materials because now you are using iron, molybdenum, and not using cadmium or indium or silver. And these materials, this is a recent paper where again the same energy level diagram of the two semiconductors has been chosen. So you choose the semiconductors knowing where are their conduction bandage, valence bandage, and you can create this heterostructure which will facilitate the transfer of electrons to one of the semiconductors and transfer of hole to other semiconductor. And when you have this transfer of electron to one semiconductor and hole to another one, you are increasing the lifetime of these charge carriers, and you are reducing the chance of recombination of it. Now you can see the measurement of the current density, right? And that is increasing in the heterostructures compared to the bare materials. You can do cycling studies, how many times you can do this on off, and which kind of shows that it is a stable material. You can use it for longer time. But of course, for real applications, you have to use for much longer time and show it is stable. This is again a Mott-Schottky plot showing you both N-type and P-type charge carriers, and which is like what I discussed earlier. This is another idea that if you can have different facets, you are making a core shell kind of structure like earlier, but now can you control the facets and show enhancement in the efficiency of the photoelectrochemical process. So here we did prepare two types of morphologies, a cubic morphology and octahedral morphology of the sodium niobate, which is at the core, and the other semiconductor, then you put on top of this. And once you put on top of that, that is cadmium sulfide. So the one which has got the cubic one shows rapid degradation of the dye. That means the reducing power is more, which means electrons are reaching there faster, and which means electron hole are not recombining. So this is a better photoelectrochemical catalyst compared to the other orthorhombic shape, which is formed by the nanoparticles having the octahedral morphology. We can do some calculations and explain why this happens based on the atoms on the surfaces which are involved in the cubic structure and the rhombohedral, the orthorhombic structure. So you can calculate these band diagrams, and you can show in one case you will have the NP junction, in the other case you have NN junction. This is not good, this is better, and this happens for the cubic sodium niobate heterostructure. And so the cubic one is better, that is what it is. This was published in 2017. More recently, we have done similar things, slightly different. We have got faceted structures, but here we have the cubo-octahedron, which are like truncated. So it's a different morphology, but idea is same, to check whether compared to a cube, what happens to this truncated morphology. And we do more detailed measurements and more detailed understanding through theoretical calculations. So these are typical SEM pictures, and you have this cube, and this is truncated cube, and on top of them, then you put the second semiconductor. Here, the second semiconductor is iron vanadate. Okay, the cube or truncated cube are sodium niobate, and on top you have put iron vanadate. When you do that, then you measure different properties like optical properties. You can see the band gap is shifting. The band gap was 3.04 for the truncated cube, and for the cube it was 3.40, which goes down to 2.20 in the uh, truncated cube FeVO4. Okay, some close to that. So you can reduce the band gap from 3.4 to 2.2 in this truncated cube by coating with iron vanadate. And then you can measure the lifetime of the charge carriers, etc., through, this is called ultra-fast spectroscopy or transient spectroscopy. I won't go into detail, but you can measure excited state lifetimes. You can measure the lifetime in picosecond. That means a sub-femtosecond, because you are using femtosecond spectroscopy using lasers. You can measure up till several picoseconds of lifetime. And that tells you where are the electrons in the excited state and how stable they are. So these are the calculations and done for the truncated cube and for the normal cube. And you can see that there is some change in this level. This is at 2.98 electron volts, whereas for the normal cube, it is at 3.34 electron volts. And these kind of changes make the transfer of electron and hole more efficient in the case where you have the iron vanadate on top of the truncated cube. So this can be shown during these calculations. You can also do surface charge calculations, and you can show what kind of surface charges are there on these different facets. And these calculations also explain why certain shaped particles have more efficiency by calculating the surface charge. So you can see the surface energy is highest for 1-to-1 planes of the truncated cube. Okay, so you can calculate the different planes and what is the surface charge and surface energy. And based on that, you can tell what would be more stable. Electron would be more stable there or less stable there. And that helps you in explaining the data which we have discussed in the previous slide. So you can have surface energy anisotropy, you can calculate, which makes the electron accumulation or hole migration, and ultimately it leads to increased donor density, stronger band bending, and stronger internal feed. So this is a more whatever I was telling you in terms of facet control for increasing the efficiency. You can also do another thing. Instead of having one shell on top of the core, you can have two shells. One is an N-type shell, another is a P-type shell. If you do this kind of geometry of 3 layers, then you can get efficient semiconductor heterostructures. So this is the 3-cell system. So you have initially TiO2, which is a UV catalyst, and then 2 mid-band gap catalysts. One is N-type, one is P-type. And so you know N and P-type create a junction and a charge barrier. And you want a barrier because you don't want electrons and holes to recombine. So the lifetime will increase as long as barriers are increased. And this you can see that for the case where you had N and P type, the photoluminescence efficiency goes down, which tells you that recombination is less, hence luminescence is less. That means you have more long-lived charge carriers. This is another example of if I have an electron sink in the lattice. Suppose I have some semiconductor particles. Here we have got cadmium sulfide supraparticles, which are like balls of 5 nanometer particles assembled together to make 400 nanometer supraparticles. If they are put on a surface of, say, graphene oxide acts as an electron sink, and it pulls away electrons when they are generated by the photons falling on the lattice, right? And if the electrons are removed from the site faster, so your lifetimes are high, and the electrons will be more useful for any reducing reaction or generating current. And that's the idea behind this. And these are all that this is something called bridge recovery. This takes a lot of time to recover. And if there is no graphene oxide surface, then it is faster. And that means the lifetime is more when you have graphene oxide. Okay, so this is what I said, that electrons get transferred on a graphene, although it's written graphene, actually it's graphene oxide. And once it is transferred there, that it is moved away from the site. That means those electrons can be effectively used for reduction. You can calculate the rate constant for degradation of dye. The dye will be degraded much faster in this system because electrons are available much faster. And that can be seen in the rate constants. This is another example. You should stop me when you want, okay, right? So this is another example where you have a hole sink and an electron sink. And this is again like cadmium sulfide nanoparticles or supraparticles. The cobalt phosphate acts like a hole sink. It takes away holes, and the carbon nanotubes used here act as electron sink. So if the electrons are removed by carbon nanotubes and cobalt phosphate removes the holes, then effectively both electron and holes are migrating away from the site of where they are being produced by the photons. And so the lifetime of electrons and holes will be high, and so efficiency of this catalyst would be high. And that's what we see. These are all different measurements to show that the ternary system with the hole sink and sink will have the highest current density. Okay, 856 microamperes per centimeter square, but the only cadmium sulfide gives only 5 microamperes. So it is several hundred times more when you have got the hole sink and the electron sink. And there are other data here. I don't have time to discuss it. Yeah. You want to say something? Shall I move ahead or?
Yeah, no, sir, it's fine.
Okay, so this is Mott-Schottky plots. This again, it shows NP junction, like you have got both the slopes, and you can see we have calculated the charge carrier density, and the charge carrier density in cadmium sulfide is of the order of 21, whereas in the ternary system, it is of the order of 22, so nearly 1 order of magnitude increase in charge carriers. Okay, so when you have the hole sink and the electron sink, the charge carriers available to you is 1 order of magnitude larger. This is another system. The previous one had a hole sink and an electron sink. Here, there are 2 electron sinks. So carbon nanotube is also an electron sink, and iron oxyhydroxide is also an electron sink. And you note these are all iron hydroxide is a very cheap material to use. So these are semiconductors, and you are using your main semiconductor is copper thiotungstate, Cu2WS4, in which you add this carbon nanotube and iron oxyhydroxide. So the carbon nanotube and iron oxyhydroxide basically pull the electrons away from the conduction band of the copper thiotungstate. After the photon produces the electrons, which is in the conduction band, it hops to carbon nanotube because it has an energy level we know by calculation. These measurements can be done using electrochemistry or using XPS and other studies, and you know where this energy level is, and that facilitates this energy to the final conduction band of iron oxyhydroxide. So electron hops to multi-wall carbon nanotube to this, and these are in very fast steps. So you can do other measurements, whatever I was telling. So this is to show you that uh, this step of carbon nanotube is around 110 femtoseconds. So these are studied using pump probe laser spectroscopy. It's also called ultra-fast spectroscopy, where basically you can study excited states. These are very fast moving electrons. They are staying at the excited states for only small amount of time. And you need very special devices, detectors, along with laser systems to understand the mechanism of the excited states. And this I did in collaboration with Professor H.N. Ghosh, who is now in NICER. Earlier, he was at INST Mohali. So there are other systems like this. I will not talk about this. I've done many systems. But let me talk to you on some applications in biomolecules. So we make nanoparticles, which are luminescent, up-converted nanoparticles. So what are up-converted nanoparticles? If you have a nanoparticle which is normally absorbing in the near IR, right? The nanoparticle makes the light go out with a frequency which is higher than the frequency falling on it. This is called up conversion. You can also do down conversion. Now, why is it important? We want to image cells, bioimaging, etc. You can put dyes and all, or dyes and all. But for several reasons, you need to have inorganic particles which are better. So we want to put these nanoparticles inside the cells so that you can use NIR radiation and you get visible light. So NIR, why NIR is useful?
Sorry, sir. We are already
Yeah,
running short in time.
yeah. So
Can you
I'll just close
conclude?
in 1 minute. So we
Yes,
are
sir.
using
Thank you, sir.
NIR radiation to because they penetrate more inside the cells. They go 3 centimeters inside the cells. And so we make up converted nanoparticles of sodium bismuth fluoride. We put it inside the cells and you can see them very clearly. And they are very stable, etc. And you can image the cells. You can make particles to go into the nucleus. You can make particles to go inside the cytoplasm. And so you can identify using focal laser microscopy different images. So various such things can do. We can, like that, we can make nanoparticles by which we can do X-ray imaging. You see, this nanoparticle is there on a stage as a film, and I can see the screw inside this capsule. This is called radio, like X-rays. We can do this using up-converted nanoparticles. This is the last example, maybe I will show, is we make spiky nanoparticles like this. Inside this, we put a drug like doxorubicin, and we can target cancer cells. So the unique thing is to make these spiky nanoparticles. These are very unique because they go and adhere to some cell membranes. And you have the drug doxorubicin. Using a chemical reaction, we can make a bond. It's a imine bond, and it is released inside the cell under certain circumstances, okay, at certain pH. And that is why it is active under cancer cells. These are all published work. So I will stop here and thank you.
Thank you, Professor Ganguly.
Yes.
So now we have time to have one question, one quick question from the audience.
So what is the efficiency of this, of the structures and microstructures that are made currently? Light converting efficiency.
Can you speak on the mic?
So, sir, what is the current light converting efficiency of these heterostructures?
So I showed you that sometimes if you have to compare with the, say you are having a heterostructure with cadmium sulfide. So in some case, the cadmium sulfide current photocurrent density was around 5 microamperes per centimeter square. And that went to 856 microamperes per centimeter square.
Okay.
So it is like 850 divided by 5. So that much time, but that is one heterostructure. So if you take another heterostructure, it may be 50 times or 20 times or 30 times. So depending on the type of heterostructure, and you have to compare with what you started with. If your core material was, say, sodium niobate, then you compare with sodium niobate. If your core is with cadmium sulfide, you compare with cadmium sulfide.
Thank you, sir.
Okay.
Okay,
Thank
thank you.
you.
So
Thank
if there
you
is
very much.
no more questions, so let's have a big round of applause for Professor Ganguly. Nice presentation.
Thank you. Thank you for joining.
Thank you very much, and see you sometime.
Bye-bye. Bye-bye.
Sir, please stay for a time. We need a photograph. Kindly unshare the slide.
Sure.
And all please gather here for the photograph. Yeah, put on the spotlight.
वो बोलेंगे कुछ वैसे उनकी दिख रही है वो
Yes, yes.
Yes, sir, that is fine. Side में करो. I'll send you the photograph, sir.
Okay. If I can leave now?
No, sir, you're taking the photo.
Sir, be there. So they want photographs with you.
Okay, sure. Go ahead.
All are coming.
Thank you, sir.
Thank you.
Thank you so much, sir. Thank you. Have a great day.
Thank you.
We'll send you the photo, sir. We'll just send you the photograph.
Yes, sir.
Bye, sir. Bye.
कैमरे से लिया या हाँ कैमरे से लिया ये भेज दूंगा
यहाँ से भी ग्रुप में नेक्स्ट सेकंड में सर
प्लीज हो जाता हूँ
जाना pointer Asim ko bolo pointer. Okay. So now we'll move on to the next session. So it is my pleasure to introduce Professor Ram Sagar Mishra from Glycochemistry Laboratory, JNU, Jawaharlal Nehru University. Professor Ram Sagar Mishra received his PhD in Organic Chemistry from CDRI Lucknow and University of Agra in 2006 under the supervision of Dr. A.K. Shaw. He pursued his PhD at IIT Kanpur, and then he was a postdoctoral fellow at Seoul National University, South Korea, 2007 to 8, and then he moved to the University of Oxford, where he worked with Professor Benjamin Davis till August 2012, and he returned to India in August 2012 and held faculty position at Shiv Nadar University. He moved to Department of Chemistry, BHU, Banaras University, as associate professor in February 2018 and worked there till January 20. He subsequently got a full professorship at JNU in 2020 and presently he's working there as a professor of chemistry in the School of Physical Sciences. His current research include devising newer ways for efficient chemical synthesis of glycohybrids implicated in various diseases using including cancer and tuberculosis. Professor Ramsagar Mishra was a short-term visiting scientist at ICMS JNCR Bangalore, and he's a member of RSC and life member of Chemical Research Society of India. He is also a life member of Association of Carbohydrate Chemists and Technologists India and the Indian Society of Chemists and Biologists. He is a recipient of Dr. H.C. Srivastav Young Scientist Award to 2022, and he also received the ISCB Professor Ramrao Mane Memorial Award in 2025. He has 5 patents to his credit and a number of high repute publications, including Nature. Without much ado, I will invite Sir to give his talk, please.
Thank you. So, thank you, Dr. Das, and I'm thankful to Vice Chancellor, Professor Ma, and Professor Pathak, Seema Pathak, for inviting me and giving me this opportunity to present some of my work. And in the morning, you have seen that in the lecture of Professor D.S. Rawat, he was mentioning something, this chloroquine molecule, which is an isoquinoline structure, is a very privileged molecule which has biological properties, biological functions. So in my today's lecture, I will be sharing you, basically I will be talking on the glycohybrids. So because you also seen in the morning that when you connect two scaffolds, natural products together, its biological properties got enhances. Okay. So what we do at the Jawaharlal Nehru University, we try to make the hybrid molecule and especially the glycohybrids molecule. So first, let's for the student for the glycohybrids molecule. If you understand this triangle, so there are some privileged cyclic molecules which are present into the drug candidates, and if these privileged heterocyclic molecules got conjugated with the carbohydrate derivatives, it enhances its biological function. What does it mean by biological function? It enhances its property in terms of the very first property it enhances the solubility, because the carbohydrates are polyhydroxy molecules, they are water soluble. Second thing is reduces the toxicity because the carbohydrates are biocompatible molecule can say. And third important thing is case by case, it enhances its bioavailability. Okay. So these three properties got immediately enhanced, and this is how you make the new bioactive glycohydrate. So while making these molecules, you develop several methodologies, several chemistry, synthetic chemistry you have developed. So while doing so, we have okay. So while doing so, if you we have developed several methodologies for making glycohydrate molecules, which is the top, is the right one. We have successfully conjugated 4-hydroxyquinoline with the 2,3-formyl glycol, and in order to get this tetracyclic molecule, which is very like pyranoquinones we say, and this molecule was having got evaluated for the anti-cancer activity in collaboration. We found these molecules they are much more potent than 4-hydroxyquinoline itself, and that is maybe because of this particular carbohydrate moiety helps to uptake of this molecule into the cellular system. Similarly, few years back, almost like now 6-7 years back, we have developed method for making these little molecules. And if you see this blue part, these are nothing, they are indole molecules, and we conjugated this indole analog with this sugar moiety, which is shown here in the red color, and these molecules is called tetrahydrocarbazolones. So we have successfully developed method for making tetrahydrocarbazolones and tetrahydrocarbazoles, starting from a very simple precursor which was prepared by Ullmann coupling. And similarly, so these are some kind of advanced glycohydrates. Then we have had some linked glycohydrates by doing a very standard clean chemistry reactions, which is copper catalyzed azide alkyne cyclohexane reaction. And we also found some of the glycohydrates, they have the material application as well. So this was the area where we were working during my Banaras Hindu University days. And then these are some examples which are shown here on the left hand side. If you see these are drug molecules in fact. And first, for example, this particular molecule, which you see having the carbohydrate moiety attached, and it's a diabetic molecule currently used. This is benzazole, it's a fungal molecule, and it's an antiviral molecule, and this is a well-known drug for the cancer, which is doxorubicin. And these are the few glycohybrids molecules which we have prepared in our laboratory. And very recently, we have made these furoquinones nalox, which having a very privileged scaffolds attached to the sugar moiety, and these are bisindolyl glycobased glycohybrid. Last year we have made, and then many more like this one, which is the triazole based glycohybrid molecule was prepared last year as well, and so many more. So these are few examples. These are few glycohybrids which we have made in our laboratories, and then in 2024 we have made this pyrazolil pyrimidinone based glycohybrids with the which is in very efficient manner. If you see, it does not require any metal, because most of the things if you see in this what I am presenting here, this kind of like host gas chemistry, because whatever methods we are employing here, one is simply using ethanol, microwave condition or thermal condition, you can make this very important molecule which is pyrazolil and analog with acyclic polyol candidate. So those of you are from synthetic chemistry background, you might be knowing that controlling the stereochemistry onto the acyclic poly chain or acyclic chain is very, very difficult. So here we are not generating or creating chiral centers, rather we are inheriting the chirality from the nature. So what are the chirality presented to nature? We are inheriting that in the interest that natural chirality may have better synchronology with the biological system. Then we have made these imidazopyrimidine analogs, again starting from these two enone derivatives of sugar, and this was the by simply using potassium carbonate. If you take these two substrates together and heat at again room temperature, and within 4 hours you get this beautiful molecule which is in the criminal. And this story was also published in the last year, in 2024. And then many more. These are the some linked glycohydrates where we have made this para pyrimidine skeleton highlighted with the light blue color, conjugated with the triazole linker. So these are the area which we have been working, and this all credit goes to my students who actually made this possible. And then last year November, what we achieved, we have made 2-deoxy sugar analogs, and because 2-deoxy sugar are very important class of molecules, I will be telling you why they are important molecules, and then we conjugated those 2-deoxy sugars with the various indole analogs, and we got bis indole derivatives. And then very recently, this year, we have developed a method for making the C-glycosylation of indole, and this is C-glycoside of indole, and we done this reaction by using the silver carbonate, which is a comparatively, naturally benign reagent. So in today's presentation, I will be sharing you the 3 stories. One is for the synthesis of 2-deoxy sugar, starting from the glycals and then these 2-deoxy sugars were further modified and were successfully by multi-component reaction successfully coupled into quinoline analog was prepared, which having acyclic polyol with a 3 defined chiral center. And this story was published January 2026. And then this one for the synthesis of C glycoside, starting from very simple precursor, which is called acetobromo sugars or acetobromo glucose or galactose, and by using very simple like halophile, which is silver carbonate here, and reaction work perfectly fine. And we have got some very interesting observation while doing this chemistry, and which I will be discussing in the coming slide. Briefly, I can tell you when the electron donating group present onto the indole nuclei, we were getting the C glycoside, and the electron withdrawing group onto this side. The reaction was, stopping here like an type of product. Then, by starting from this glycal, which is in green color, the 4-hydroxycumulin, they were successfully coupled like a kind of type addition fashion, and we were named this fluorochromium analogs. And this story was published December 2025. So the first work was done by my student Kavita, and and she has actually recently submitted the thesis. And why we were interested in these 2-deoxy sugars, because you might be aware about a molecule which is called 2-FDG, and which is 2-fluorodeoxy glucose molecule, and this molecule very much is the diagnostic. Okay, so and very recently during the COVID time, there is a molecule which is called 2DG. 2DG is nothing but this is called 2-deoxy glucose, and this molecule was getting utilized for maintaining no oxygen level. The maximum test was happening during the COVID time because of the lower, this is oxygen was getting lower into the plant, into the population. So then DRDO actually have identified or repurposed this particular molecule for maintaining the oxygen level. So therefore, 2-deoxy sugar very, very important. So they are also present in many antibiotics. The 2-deoxy sugars, they are very important molecular scaffolds and which has biological properties. So therefore, many groups around the globe, they were interested to develop new methods for making that 2-deoxy glucose or 2-deoxy sugar like this, where all the hydroxy are maintained, only the 2 position, it is this hydroxy has gone. This has been replaced with the hydrogen. Therefore, this is not 2-deoxy. And not only that, many heterocycles like quinine-based or quinoline-based heterocycle molecules, so they are the class of molecules which are biologically relevant. So we were interested to develop a method for making the 2-deoxy sugars and also utilizing those 2-deoxy sugars for the synthesis of something relevant which is quinoline analogs. Okay, so so these are the some literature reports, and there are many methods for making the 2-deoxy sugars already in the literature. The work which is shown here. So this was by using anhydrosuccinamide for treatment, two-step process. The 2-deoxy sugar can be prepared, and this work was reported in 2000. And basically, this whatever the synthesis I am showing here, they are from 2000. Earlier, after there are few methods reported from sugar. The 2-deoxy glucose is not new molecule, it's old molecule. And the another one, this one, this is almost same method as it was reported in team A. So here they use a 3-step procedure like an bromosuccinamide followed by an nickel and then global deprotection of enzyme group was able to make a 2-deoxy glucose. And this method is already patented actually. The US patent. Then there is a patent reported by a British group where they used 8 molar HCl and infused it in water. They were able to make the 2-deoxy glucose, and they reported this was the paper where they are trying this as a precursor, and only 2 example has been reported. But unfortunately, when we were trying this reaction in our laboratory by using 8 molar HCl, this paper, it was not reproduced. Then in 5 steps starting from NH glucosamine, galactosamine, 2-deoxy galactose has been prepared, and very recently in 2003 from Banaras University, the Tiwari et al. What they have done by using trifluoroacetic acid and when 1 dioxide in water at 30 degrees centigrade, overnight reactions they were able to make the 2-deoxy sugar. Okay. So here what you see in the common, so the common is the starting, which is called light. And then this is another one which from our group. So this work which we have done here, we use trimethyl chloride and one good commercially there is 1 good dioxide and we heat it in 30 degrees centigrade within an hour. You see it's 16 hours here. It is very corrosive trifluoroacetic acid. TMS chloride 1 hour 80 degrees centigrade to able to make this 2-deoxy glucose analog. And then this 2-deoxy glucose analog was successfully converted into quinoline derivatives in multi-component reaction manner. So the first step was the reaction optimization. That is very standard procedure in organic synthesis or in methodology development. What we have done, we have tried several reaction conditions, like without using the by taking the pH at room temperature at 24 hours, by using TMS chloride, by different solvents at elevated temperature. At pH of 80 degrees centigrade within 1 hour, we were able to get the 81% isolated in the pH solvent was working. It was fine. Then we thought, how about using the co-solvent system? So when you use the water as a co-solvent system, because the solubility was poor of this particular substrate, 1A, it was dropped down. And then we thought using the isonitrile, still the same. And isonitrile water somewhat got improved. But what we found in this study, the 1,4-dioxane at 80 degrees centigrade yield was excellent, which is 98%. Rest of the condition, yield was acceptable, and but this was the best yield what we found. This is how we concluded that 1,4-dioxane, commercial grade 1,4-dioxane at 80 degrees centigrade, within 1 hour we were able to bring the 2-deoxy. Because when someone works on the carbohydrate chemistry or sugar chemistry, and sugar molecules are very complex. We study in the MSc class that the glucose molecule itself is split. One is pyranose form, other is furanose form, other is Fischer form, open chain form. So sometimes you get confused what's the form between these things. Basically, it is in all three forms depending on the solvent, and this remaining impurity. Okay. So similarly, carbohydrates are so complex molecules. You know what is the taste of glucose? Glucose is sweet. Glucose is when you just simply change one of the stereochemistry from equatorial position in case of glucose E4 to axial. The galactose it becomes galactose. Glucose and galactose are the equinox. carbon 4, 51. And what is the base of galactose? Galactose is not sweet at all. Okay. So by just changing one stereochemistry, it can put biological property, biological function, molecular recognition, and even its synthesis in chemistry also got complete. If we take one protecting group, one protecting forming, same molecule, different protecting group, product is significant. The neighboring group participation, if you take ethyl group at 2 position, you can decide the benzyl, you started getting mixture. So what I'm trying to convince you that the stereochemistry and protecting group is very, very important to get the carbon. Therefore, when we look the substrate scope for this particular method we have developed, we look the different protecting groups like benzyl, propargyl, and allyl, and they were all successfully converted to their respective 2-deoxy sugar analog, and we got all sugars like this is the case of glucose, and then you see galactose also. Okay, all substitution in glucose, lactose base, and then Arab nodes and D-Arab nodes, they were all successfully converted into their corresponding 2-deoxy sugars. And we were fortunate enough we got official structure of the compound, and this all the structures are not that complicated. They were already confirmed by 1D and 2D NMR, but we also further confirmed by the single X-ray crystallography. And once we have developed this method, next was to find the application of this molecule. So if you see these molecules, so here the one which is shown as a pink color. So this hydroxy actually is not actual hydroxy group, rather this is hidden aldehyde group. This is hemiacetal. Okay, this lone pair moves like this thing got open, you have OH here, you have double bond. So this is aldehyde group. So we thought of using this aldehyde group for further converting into reducing and then propargylating it, and then by 3-component method by using amine, aldehyde, and alkyne, and doing by using different catalysts, we have cleaned up, and we found one condition which was this copper triplet one, and 0.5 copper triplets within 2 hours we are able to build this particular substrate. So then we look the substrate scope for this transformation as well, and if you see here all different sugars. So here this curly bond doesn't mean that this was a mixture of 2 isomers. This simply means that we have tried both type of stereochemistry for this particular transformation, and in all cases if you see alpha and beta, and also beta and alpha. So all different type of stereochemistry was maintained at the acyclic chain, which is very, very challenging if you try to make the chemical synthesis. And with this, we have proposed mechanism for this transformation, and we also done some control experiments. So proposed mechanism is trimethyl chloride, kind of sustainable release of HCl, we can say, in presence of moisture, which was present in the 1,4-dioxane, therefore commercial grade. The HCl is getting generated, and yes, HCl is the reagent, you can say, in this transformation, which is participating and getting 2 positions protonated, and the lone pair pushes back, and then OH water molecule attacks back, oxocarbenium ion goes back here, then molar plus with the 2 sugar. Then, as I mentioned, this is a hidden aldehyde group, which was reduced by sodium borohydride, followed by the propagylation, which was the substrate 3A, and which was coupled with this amine and aldehyde, and finally copper catalyzed cycloaddition reactions, and the final compound 6A formed. So this is how we completed one story, and quickly I can complete my second story. So this was the story actually initiated and completed by this gentleman, Rajiv Tyagi. And what he actually, in this particular work, one thing I should emphasize that, the C-glycosylation or glycosylation is the reaction which is well known from very, very long period of time. And what we have systematically done here, we have took the different H2 glucose and galactose, and we try to react with this indole derivatives having the C3 position and different substitution at R1 and R2, and having different substitution at aromatic. And what we found, And why we were interested of making these molecules? Again, this is the background, this is the introduction, you can say. The C3 glycosides of indole, they are privileged scaffolds. Or why? What are the privileged scaffolds? Privileged scaffolds are those scaffolds which are present into the drug molecule, which has some biological function or biological activity. And if you see here, so these are the different C glycosides at different positions. This is like C3 glycoside, this is inhibitor, this is C21, and it is also C21. So all different, you see, they have indole nucleus, they have the sugar moiety. So therefore, we wanted to make this one. So C3 glycosylation, many people actually have been working on it, and many people develop few methods for the this C3 glycosylation. The very first one, if you see written as scheme A, where the palladium catalyzed reaction for the C3 glycosylation was reported, the yield was poor. Then another one, which is indium chloride, developed by J.R. Mukherjee and Propyl Jammu, and this substrate works with the limitation of this was only style protected sugar was working. Then this is method developed by Pintu Mandal in the Lucknow. So, and what we did, he used the B6 to this particular acid by trifluoroestamate chemistry, they were able to make C3 glycoside. Then another one by the Chinese group by using this protein-based reagent. Then by using different donors, this was done by conventional like Guwahati. And if you see all these methods, they are very fantastic methods. Broad substrate scope and analyze, but their limitation is, they are using some reagents which are corrosive in nature, number one. And for example, this economic one having this donor here, so they are not atom economical. So what we have thought, using simple donor, although this is very much expensive, and by using the silver carbonate as a halophile, we develop a method for making C3 glycosides. Okay, so this is again the external optimization for this particular transformation. If you see compound number 1, which is L-rabinose, and this was reacted with the compound number 5, which is 2-phenyl indole by silver carbonate. So anhydrous solvent is very much required for this particular transformation. If that is one limitation, you can also say. But if there is no anhydrous solvent, so here you get bromine and replaces with the hydroxide. So under anhydrous condition, we have tried different conditions. The best condition what was reported here, almost same, but here equivalent are higher. Carbonate. So we thought we have proposed that number 8, where one equivalent of silver carbonate was utilized for this particular reaction. Within 2 hours, at the room temperature, we were able to make this. This is C3 glycoside in very highly distereoselective manner. Because if you see here, because the two possibilities either this dual equatorial or some axial, but we are getting exclusively the beta selectivity because of the labeling group participation presence of acyl group at 2 position. So then various sugars like glucose and galactose. So this is L-rabinose with the different substrate scope with the different substitution as the indole moiety, where you have phenyl, where you have methyl or methyl, electron donating or electron withdrawing group and the aromatic ring. They are all successfully converted into their respective C3 glycosides. And again, we were fortunate enough that one of the compounds was well, it was number 1, this one, we got the crystallized and we got the crystal structure where the beta selectivity, although that is not very difficult in this class of molecule when you do the 2D NMR, because the beta selectivity you can simply confirm by the coupling constant, because this is axial and axial. By using diaxial coupling constant, you can confirm, but we have confirmed by the NMR as well as to the X-ray crystallography. So here, when we move to the hexoses, because earlier was pentose, this arabinose is pentose. When we move to the hexose, what happens? What happens here? What we found very interesting result, that when there is electron withdrawing group present onto the aromatic ring, okay, so like methoxy, we were getting C3 glycoside. Okay, when there is electron donating group were present, we were getting C3 glycosides. But when there is electron withdrawing group like Cl and Br were present, in case of hexoses, we were getting these kind of structures, and these structures were again confirmed by the proton NMR and single spectroscopy. And what was the difference? If you see the number of carbon, number of proton, even molecular weight is same. So, but there is a difference in there, the chemical shift of the carbon, which is very difficult to actually see, because when there is a style group are present, you see very clearly in 13 CNMR, 4 carbon around 21, between 21 to 20, starting from 20 to 21. When this got converted into orthoester, like this one, this particular methyl group got shifted around 25. Okay, so we saw there's some unusual pattern into the C13 NMR. So therefore, we have relooked the structure carefully and analyzed that. Then we found these are structures, and this method, and then we have done some DFT calculation in collaboration with Chatresh, and we found we have the answer. We have very clear cut answer why, when there is electron withdrawing group is present, why we are getting the orthoester type of product. When there is electron donating group, why we are getting the C glycosides. So all details are in this paper. Because of the lack of time, I'm not explaining each and everything, but this methodology works into the disaccharide as well. When again the same thing, when the electron withdrawing orthoester, when there is electron donating, we got the C glycoside, and this is the proposed mechanism for this particular transformation. Esteobromoglucose, the silver carbonate, take off the air out and we drop the carbonamide, the neighboring group participation, two, and now the node nuclei approaches this one either from the C side or directly from N side. So when the electron donating group are present, the C was present, and the electron withdrawing was present, N was preferred preferential attack, and we're getting the N orthoester type of products or C glycoside products. And the last story quickly, this was done by Preeti, and she is faculty in one of the college in Delhi University, Shivaji College. So she had developed method for making these furochromin analogs, and this work was published in December 2025. So I will stop here. And actually, this furochromin's molecule, they are very important class of molecule because present in many natural products. You see all these sectors here. For example, this cholesterol, furolone. These are all natural product molecules. They all have the furochromin scaffold. Therefore, many methods have been reported in the literature for making these ones. So I am not the first one. But I am one of them to make these furochrominins. Structure were well established by X-ray, NMR. This is the proposed mechanism, and this is how we have concluded that we have developed method for making 2-deoxy sugars and also 2,4 substituted carylipure based glycohydrates. And we were effectively working in last like 10-15 years on the glycohydrates molecule, and we found some very good result in terms of their biological properties, which I am not presenting here, and because still work is going on. And I'm thankful to my all students who actually contributed this work, a work which I have presented onto the 2-deoxy sugar done by Kavita, and with low C glycoside by Raji, and then last one by Preeti. And thank you very much. This is my new laboratory at the JNU, which was supported by Saint Sagnaria. Actually, this is not just impressive, there is a purpose of showing this particular slides, because I want to show the picture of that gentleman who actually contributed. And this is the first batch of chemical when arrived in my laboratory. So I am standing here. So I'm very much happy that I can start some work. And this was the late 2021. My son is standing next to me. And yeah, so this is the gentleman. You see you might be many of you might be recognizing him. He is the Saint Sagnaria. He's an industrialist. Actually, he has donated all the furniture to my laboratory to establish because I moved from the BHU to JNU, and in the university system, especially in government system, it's very difficult to establish lab in a quick time, because it will take 5 years or something. It's not like in IIT. In IIT also difficult nowadays. So, but my laboratory was very smoothly established by this gentleman. So I am very thankful to him. Inaugurated by then Vice Chancellor, and this is the first batch of students. Very much happy. Marx from Germany has visited that time. So thank you very much. And this is So this is the slides. This is my PhD supervisor, to whom I have learned a lot of medicine chemistry at Lucknow, Dr. Keshav. He was very much happy. He has visited me, my office, and you can see Malviyaji is there. I bought from the, I took him together from the BHU, and yeah, so this is the last slide of my presentation. This is one of the statue of Swami Vivekananda. It is standing in the middle of the campus, and there was a lot of protest actually to have this statue in the JNU, unfortunately, but finally it is there. So people comes and have the selfie there. Point. So then thought, why not we as a group go and have the group photographs? So this is my current group at the JNU. Thank you very much for your time.
Thank you so much, sir. Now I would like to invite Professor Seema R. Pathak, our HOI, to facilitate Professor Ram Sagar.
And if you have any questions, please you ask.
Yeah.
सर एक क्वेश्चन था
Okay, one question we have. Yeah.
सर अगर आपने जो मॉलिक्यूल बनाया
Sir, your audio is not coming. Hello. Hello.
Institute of Technology. And yeah, so next speaker is Dr. Sudipta Roy from IIT Delhi, and he actually done PhD in Naipur, Mohali with Professor Asit K. Chakrabarti, and he joined IIT Delhi in 2018 as an assistant professor and was promoted to associate professor in 2023. His research focuses on sustainable catalysis for a small molecule activation. He is a recipient of several prestigious recognition, including the Marie Curie Individual Fellowship in 2018, PBC Fellowship in 2014, and CSI Research Associate Grant in 2013, and the Eli Lilly Asia Outstanding Thesis Award of 2012, along with the OCS ECR 2024 Lecture Award sponsored by Willy. So his will be speaking on the utilizing renewable energy to functionalize CSP2S bond for the synthesis of value-added compounds. So now I invite Dr. Sudipta for his talk. And I request Dr. Sudipta, as soon as finished, we'll go to home.
Thank you, Professor Ram, for your kind introduction, and thanks to all the organizing committee to giving me the chance to come here for the first time, and I'm really thankful for the hospitality. So, since it's conference is more related towards the sustainable development, I thought to present something which actually we are doing from last 5 years and so on. So, how actually we synthesize this molecule with utilizing the renewable energy. So I thought that to present that one in front of you. Okay, so it is, and already we came to know that if we want to utilize the energy, so best source of any energy is nothing but the sun only. But unfortunately, whatever the amount of the sun energy we got, we are not able to utilize it. Even if we able to utilize the 1 hour, that is sufficient to really run our whole community, our whole like human civilization, we can run it. But unfortunately, we cannot utilize the whole energy of that sun one. But nature certainly it utilizes it in a very intelligent way. If you can see that one, certainly whatever the eyes we are blinking, that basically you will see because of that some photochemical reactions also, and whatever the food we are getting from the photosynthesis, there is a certainly involvement of the sunlight over there. And there is also like a oxygen, it is converting into a ozone, and because of that one only probably we are not all affected with the sunlight whatever it is happening over there. But this is really mother nature knows how to work with the sun over there. But when it is utilized into our laboratory, how we'll utilize that one, that is the main concern over there. And most of the cases it is not actually that we are able to utilize the photon energy. The reason is that one, not all the molecule it absorbs the light. So if it is absorbed the light, what will happen, it usually goes into the excited state, and then there is a possibility that it will relax into this other state only. And if we get a chance, particularly at this excited state, then we can do some chemistry over there. But unfortunately, all the molecules are not active at that positions, or like all the molecule not absorb the light. Then how we can do it, how we can deal with that one? So that is the possibility that we can use some photocatalyst which actually goes into the excited state in presence of a light. It will absorb the light and then it will interact with the substrate as I mentioned over here, and then we can do some chemistry with that one only. Important thing is that on or whenever who is working on this photocatalytic system, actually they want to develop a catalyst system like just like a metal catalyst one. So that means we can like spread the both hands. For example, I can do the reduction as well as I can do the oxidation from the single catalyst only. As I have shown over here, this photocatalyst can go into the excited state and it can take one electron from the reagents, then it will form a radical anion of the photochemical species, and subsequently it will transfer to electron to some other species and it will revert back to this photocatalyst, and this way it can close this photocatalytic cycle over here. Other thing it can happen that the excited photocatalyst it will actually give one electron to the substrate, and then subsequently it will take electron from the other species and particularly complete this catalytic cycle only. What I mean to say, like a metal, we know that one Like a palladium, I can say that palladium goes to the +4 oxidation state, palladium go to the +2 oxidation state, again coming into the 0. That means metal have that liberty to control this electron oxidation as well as the reduction over there. But when you think for the organic molecule, barely you will see some molecule which will oxidize as well as reduce simultaneously, and it will act as a catalyst over there. So that is the key essence of our lab. We try to utilize, we try to make some molecule in organic particularly, which will actually do the both oxidation as well as the reduction over there. So if I think about the challenges, these are the all good part of the photochemistry certainly, but there are some like a major challenges over there. If I see into that one only, as I mentioned over there, once you are utilizing this photocatalyst over there, as I mentioned, so you need something which actually close this photocatalytic cycle. So that means you need a sacrificial oxidant or the reductant to complete this photocatalytic cycle. That means whatever the things you are chemically you are using, you don't need it. It will not convert into the product, but still you have to use it just to control the catalytic cycle. So can we somehow control that one? Can we use that one, or can we don't use that one, but still we can close the cycle over there? So that means we can do some sustainable development over there. Another major problem is that one here, redox mismatch. So whatever the chemistry you are trying to say about that one, you are thinking that your excited state photocatalyst will oxidize or the reduce over there. Yes, indeed it is possible, but it will possible only when there will be a proper matching of the redox potential. If they are not matching, then reaction will never happen over there. So that means, in other words, I have to broaden the window of this photocatalyst so that I can oxidize or reduce whatever the things I want. But so far it's not so simple over here. The another major problem is that one, we know even that one, the scale up possibilities, because those who are working on photocatalysis, they know you can always work on the small scale. If someone asking you, okay, make a 500 gram reactions or 10 gram reaction, I will not able to do that one. So how we can overcome those challenges over there? So these are the main major challenges with the photochemistry. So today only what I will try to explain it, I will try to explain how I can broaden the reaction windows actually, so that you can oxidize whatever the substrate you want over there. So as I mentioned over there, so we are trying to mimic the metal catalyst. So that means a catalyst which will be able to oxidize as well as reduce at the same time. So there are some actually potent photocatalysts is already known in the literature. If you see that these photocatalysts, they are very much active at a reduced condition. That means they are strong photoreductant. On the other side, you can see that these catalysts, they are strong photooxidant over there. That means if you just want to oxidize specifically or reduce, you have a chance, you have a liberty that you can do separately. But what if I ask you that, okay, you may give me one catalyst which will do both these catalysts simultaneously, strong oxidant and the strong reductant, you will not have that much strong like a library. In that case, you can see some examples here. Both these catalysts, they actually work in both the ways, but you see the excited potential there is relatively low over there. So here is actually we pitching. So we try to make a catalyst which will actually solve this problem. How we can make a catalyst which will have a strong photooxidation property as well as a strong reduction property over there. And if you see this, particularly these molecules, you will see that those who are working as a photoreductant, if I go back again, you see this particularly amide or amine moiety, they are acting as a photoreductant over there. And particularly once you are having, for example, let's say the keto type of moiety or like a cationic species, they are acting as a strong oxidant. So we thought that if we combine probably both these two molecules, it may act as a both photooxidant or the reductant. So Partho take this actually like a opportunity. So he make this class of molecules, sinulins molecules, and this particularly this molecule, once we have recorded the CV, we can see that it actually able to oxidize or the reduce over there. And fortunately, this also absorb a visible light. So which means what I can say that this molecule will go into the excited state, it can do both the oxidation as well as the reduction over there. So that was our hypothesis. We thought that it will certainly it will work. And once I have measured the lifetime, I can see that it is having a 5 nanosecond time. So that means it is sufficient enough to do some organic chemistry over there, and it is going up to like a 2 volt over there. And whatever I have shown, it is even much better than that one. So now it has time to check whether really it is oxidizing or acting as oxidant or not. In that case, we have taken a very simple molecule. We have taken a aromatic amines, for example, like a benzene derivative, without any like a leaving group over there. And particularly, we can selectively able to functionalize the CH group over there, and we are interested to make a CN bond formation over there. We are interested to make a isolations. So you can easily isolate with the particularly the electron rich aromatic species over there. Then you try to make the reduction chemistry. In that case, we have taken a bromoacetophenone derivative. In that case, bromoacetophenone derivative also it was slightly challenging. You cannot reduce it so simply. So, but our catalyst will able to do that one, and you can get your parent acetophenone over there. That was the just proof of concept. How we can make like your catalyst can work both as a oxidant as well as a reductant over there. These things. But when we try this chemistry with a simple benzene molecule, unfortunately it was not working. That means we know that one, even though we get a photocatalyst which act as a both photooxidant and the reductant, but this is not strong enough. So how we can again improve this photocatalyst over there? So we lost someone. No, battery.
Current है.
The audio is not coming, so kindly check the audio, please.
Yeah. So if I try to oxidize some benzoic acid also, so you need or you have to go beyond this plus two system. So that was our motto, how we can develop that catalyst system. Particularly, you are interested to make a aryl radical. So I have shown only the CN bond formation reactions. If you are able to make this aryl radical, you will have a liberty to make CN, CB, CC, all sort of bond formation. You can do that one actually. So if I see, as I mentioned over there, so the first generation catalyst what we made, it was not so successful over there. So then we thought that how we can again improve our catalytic system to that one. And then there is already known in the literature that particularly this type of polyaromatic system, they worked as a radical generator, but you need a strong like a, for example, metal or the high temperature over there. And we are particularly interested for this fly molecule over there, because this molecule was never explored in the excited state over there. So we thought that if we are able to excite this molecule, possibly it can show in a different way actually. The reason is that one, because if I see the molecular level or that one, you will see that it is having an in-bonding molecular orbital over there. So particularly we try to hit this molecular orbital, and if I reduce it, I will make that one this radical anionic species, and that was proven by the CV also. I can see that I can precisely make a single electron reduction of particularly this photochemical species. And after that, if I shine light, and moment we have taken this UV, basically we can see that it can absorb light in the visible region over there. So that means our motto again was that we try to make a molecule which will absorb the light as well as we will able to reduce it over there. So that means this already molecule having this property over there. And if I shine light, particularly after reducing of that one, then what will happen? You will inject this electron, or you will promote this electron to the higher high electronic state. So that means you will make a super reductant, particularly after reducing it that one. And even if you don't reduce this photocatalyst, if it simply absorb this light, at that time also you will create a hole at the lower lumo. So that means in presence of a light, you can make a super oxidant as well as a super reductant, particularly with this type of catalytic system also. Now then we thought that why not to use it as a photocatalyst, and we have measured this excited state potential. In that case, you can see it is already close to this 2 volt, which means like it can able to reduce our aryl halides over there. And then we try to reduce this aryl halide species, particularly in presence of a DBO or DIPA. You can see that it can completely reduce our aryl halide species over there. Then I try to measure, or I try to understand the mechanism, how things are working over there. We have taken this 3 class of photocatalyst over there, and you can see that in a ground state, none of this catalyst will able to reduce this particularly aryl halide over there. So if you want to reduce it, it must have to go to the excited state over there. So that's the thing only. We propose that okay, first your photocatalyst is going into the excited state, then you are making this radical anion species, and this radical anion species is going into the excited state, then only actually involved in these reactions and actually involved in the reductions process over there. So then some sort of small calculation we have done it, and from small calculations also we like we have shown that it actually needs to go to the excited state, then only it will able to do this chemistry over there. So during the UV visible studies, when we start adding the base in the presence of a photocatalyst, we can see that one peak is generating over there. So we try to understand why this peak is forming over there. So then we try to visualize this, let's say this type of complex in computational, and we can see that they can form a 1:1 complex over there. So, and interestingly, once we have checked the lifetime in after shining the light, we can see that lifetime is increasing over there, which clearly tells that new species is forming over there. To understand that which new species is forming over there, we have done the EPR study. In that case, we can see that EPR signal is increasing once we are increasing the like a intensity of the light or the incident lifetime also over there. So that means it clearly tells that in presence of a light, you are making certainly this radical anion species over there, and this is more stable one. You can play around with this particularly radical species over there. So to further prove it, why we are actually getting this peak once we are shining the light over there, then we have done the photoelectrochemical studies. In that case, what we have done, we try to reduce this plasma molecule in the electricity, and we can see that the new peak is appearing over there. Once we have done the reverse scan, that means we have run from minus 1.5 to the 2 volt. At the time this peak disappeared, and again it is appearing over there. So that means the peak what is forming, particularly in this case, this is nothing but the radical anion species, and it is a reversible peak. That means you can give an electron to this particular species, and again you can take it from the that species also. That means it can act as a perfectly catalytic system over there. That is the things only. So, and it is so light specific that even you want to reduce it, it only work with the blue and the purple. The reason is that on in all both these cases, you have to first excite your photocatalyst, then you have to reduce it actually. Okay, so and your light should be in such a way so that it overlap between these two species only, then it will work, otherwise it will not work. As you can see, our chemistry is working in presence of a blue light, but it is not working in a green light over there. So, okay, so that's already I have discussed over there how this chemistry is working with the aryl halide, and then since it's not only it's not only the like a CH bond formation from the CX bond, but we can make the CC bond, we can make the CP bond, we can make the CB bond, as well as we can make the reductive arylation only from the single catalyst only. In a one pot we can do all this type of chemistry over there. Okay, so as I mentioned, so our main intention in our lab is to make a catalyst which will go beyond like a +2 volt. So in inorganic chemistry, we have learned that if you make a ligand to metal charge transfer, at that cases only you no need to cross the barrier of this redox potential. So that was the same thing we tried to do that one. So our plan was like that. Even we have seen it before that our photocatalyst is actually interacting with the amine moiety. Then we thought that THF molecule, which is actually difficult to oxidize, if it form a complex at the excited state, again we can do a very similar to the transition metal type of behavior. We can mimic the metallomimetic charge transfer process, and then we can make the THF radical actually. And if we are able to make this THF radical, already we know that how to make a azole radical or n-center radical. Will club these two things, and then we'll make these CN bond formation reactions. That was the idea. Then we can make it or call it as a metallomimetic charge transfer process, and indeed it happens. Like if you take a azoles and then if you take a triazoles, in that case you can make this CN bond formation reactions.
conference
Okay. So Onukriti did this one. So she took the challenges. So she slightly modified the catalyst. If you remember the previous catalyst structure, now you will see that we have just slightly modified. We make a salt of that one. So that means we are again pulling down this NB non-bonding molecular orbital. It is making it more like a super oxidant over there, and then we can easily make this carbon nitrogen bond without using any catalyst, just in presence of a light. So then after that, Partho, what he did, as you remember in previous cases, once we make the sinuil in our first generation catalyst, at that time we are unable to oxidize this benzene ring over there. But in this catalyst system, now we can oxidize it. We can easily make the azole, and then we can simply club this benzene ring and that azole one. We no need any leaving group like for example triplet or aryl halide or aryl bromide. Simply we can make the like a selective CH bond functionalizations over there. Not only with a benzene or like a azoles, we can make a several types of azole. We can make it, but the like a regioselectivity, particularly it's the intrinsic property of the substrate. It's a not the inner sphere mechanism; it's outer sphere mechanism. So certainly the electronics property of the substrate is actually dictating the regioselective outcome over there. And as you can see, we can take a different heterocycles also. In all the cases, you got a very good selectivity over there. So then we move further. So we thought that why not to break this CF bond, because the CF bond is relatively much more difficult to break. In that case also, even though yields are not so impressive, but still with our catalyst we can break this CF bond and then you can make these adulations reactions over there. So that is the schematic diagram how this chemistry is working. So both way it is working, it is actually oxidizing both your aromatic ring as well as it is oxidizing your azole moiety, and subsequently once a radical are forming, then it can club together. So because we have used two different solvent, in two different solvent it actually work in a two different way over there. So as I mentioned over there, so we know that on how to oxidize particularly the benzene moiety, then we need to check whether it will able to oxidize this acid or this thioamide also. Indeed it works. So you can oxidize your acid moiety, then make such type of coumarin moiety, and you can oxidize your thioamide part in presence of this catalyst and then make this benzothiazole as well. So as I mentioned, particularly today what I have shown you, I have tried to mainly focus on that design of this photocatalytic system over here. We are not only working on this system, we try to work on some other system as well, like for example the autocatalytic system. For me, like if you using a less, then you are contributing more towards the green chemistry. So if you are don't using even a catalyst also, that will be much more green chemistry over there. So some of the molecule in presence of the light, simply you can make those things. And in as I mentioned over there, if I try to remove the oxidant or the reductant, so electricity or the electrochemistry is the best way, that one. So with the using of electricity, you can simply like knock out your oxidant or the reductant, and that's what we do sometimes. Like we try to club the photo and electricity to make some new molecules, and we can easily go through that one only. So today what I have told, so like I told that we made our first generation of sinuline catalyst. In that case, we make all sort of CN, CP, CP bond formation reactions over there. And once we make this ply molecule, this ply molecule also, we try to oxidize like a usually the challenging one, like those who are having a potential more than 2 volt, we can do that one. And ultimately later on I have shown that that okay, you can mix such type of metallomimetic charge transfer process to make a radical coupling over there. So behind the screen, those who are mainly working, they are my hardworking students, and of course the funding agency, those who support our funding. And thanks for your kind attention.
Thank you, Dr. Gupta. Now, floor is open for one quick question. So, if there is no question,
organic catalyst is reusability. Yeah. So usually you do it in a homogeneous state. So reusability is a problem, and that is why metals are better. So have you tried to incorporate these into, let us say, polymers or something, so that they can be used as a heterogeneous reusable catalyst?
Yeah, that is a good suggestion. So far we have not tried it actually. That's a good suggestion. Yeah. But we have seen that there is a photo bleaching. We have seen it. But sometimes some reaction depend on the solvent, which solvent we are using. In that case, it shows up to 2 or 3 cycles, but after that it is completely dead. That is true. There is a photo bleaching, strong photo bleaching is there. I talked with Lina to make with a resin, because we are having already phenolic moiety. If we
Dr. Chandramohan is not there. He is an expert in polymer chemistry. Like he's really an expert. So maybe we can think of some collaboration.
Because we are having phenolic moiety, because one is also work on benzylic like a moiety. Make that one. We thought that if we do some reaction, then it will be hooked into that resin moiety, and then might be it will work at that one. But yeah, heterogeneous it might work actually.
okay. So if there is no question, so let's have big round of applause for Sudatta talk.
Thank you, sir. Now I request Professor Ram Sagar and our HOI to felicitate Professor Sudipta for a moment. नहीं ये है फोटो फोटो नहीं जागृति मैम प्लीज आप भी जाइए कोई दिक्कत नहीं आप प्लीज प्लीज
Yeah, so next speaker is Dr. Jagrati, and she is from the NIT Srinagar, Uttarakhand, and with over 13 years of teaching and research experience, she specialized in the electronic structure and calculation and gamma rays and scattering with the expertise in first principle methods such as FP, LAPW, LCAO, and SPR, KKR, and she earns her PhD in 2012, focusing on electronics and magnetism property of advanced material, and her research spans electronic, optical, and magnetic property with the recent emphasis on renewable energy, material, and photovoltaics. Dr. Sharia has published more than 100 research papers and contributed 10 book chapters and edited 5 books with a leading publisher like CRC Press, Elsewhere, and Springer. She has supervised 3 PhD scholars and is currently guiding 4 more for the PhD degree, while also leading fund projects from SERP, CSIR, and an active academician. She has delivered numerous invited talks, organized academic events, and served as a reviewer for several reputed international journals. So she will be delivering her talk on computational design, multifunctional perovskite for sustainable energy, bridging photocatalysis, and opto optoelectronics. And so now I would like to request Dr. Jagrati for the presentation.
thank you sir for the nice introduction and I am pleased to present my work in this conference. The theme of the conference is very much related to the current scenario as we are witnessing the continuous intersection between the science, sustainability, and the global challenges that we are facing in the energy sector. In recent time, we all have seen the energy supply chain globally is completely uncertain, and the recent conflict that is occurring in the Middle East, especially between the the America and the Iran, it has again highlighted the importance of the
Ma'am, if you
conventional energy sources
also.
especially, and this all thing impact our country especially because it impact our energy security, it cost and the stability. So the thing is how to become the how to become the energy sustainable system from the energy dependent system, and the solution to the problem is the materials. We
Ma'am, if you
need to design the materials.
ma'am, if we have a PPT, then please share online also.
Okay.
On Zoom also, ma'am.
happened there? Yeah, it should come. Already shared. It is not visible here. Don't we? No, no. They did. Sure. Yeah.
Ma'am, for moving up, just press arrow keys.
We are doing that. नहीं की हुई है स्क्रीन शेयर कर रहे हैं इस पे नहीं आ रहा शायद वहां तो लिखा वी आर डूइंग स्क्रीन शेयर हाँ शेयर कर दिया है जब शेयर कर रहे हैं वहां की पर हम Okay. So the solution to the problem is the material. We need to design the materials which can solve the energy requirement or they can fulfill the energy requirement. So we need the energy material because there is rapid increase in the energy demand along with the emission of the carbon dioxide. In this graph, you can see that in our country, both the things are continuously increasing. So we need the clean and efficient technology solution. Whatever material do we use with the help of the to achieve the energy requirement, the current technologies are some silicon-based solar cells which are in the market. We use some oxide-based material for photocatalytic activity, some different semiconductors and the thermoelectric materials. But the energy generated through all these alternate sources is not sufficient to fulfill our requirement. Along with, there are certain limitation of these technology also, including the efficiency issues, stability issue. If we are using the some material which have the lead content, so it will be toxic also, and the large scale production is again a problem. So the solution to this is we need to look for the different kind of the material. One class of the material which is promising in this sector is the perovskite material, which are the material which have a specific structure ABO3 type, where A site is occupied by some large sized monovalent or divalent cations. B site is also occupied by the smaller transition metal cation, whereas at the O site we can have the anion of the oxygen and the halides. What has been observed is that if we distort the structure of these perovskite, their applications or their properties can be tuned easily. So what can be there if we distort these material by tilting octahedrally or cation displacement or octahedral distortion? It has been observed that their energy gap, their electronic property, their optical properties can be tuned. Along with that, their carrier separation can also be enhanced. So this all provide the specific properties or the beauty to these perovskites that their energy, their application, their properties can be tuned as per the requirement. Because of this, they are widely used in photocatalytic activity, where they are used as the for the hydrogen production and the CO2 reduction. And in the optoelectronic, these materials are used in the solar cell and the photodetectors. along with certain issues. That is again the stability. If the lead is used, that is what the toxic material, because the lead based perovskite has been found a large amount or the good efficiency is observed, but their toxic nature is not suitable for their practical application. So the solution to this is what the double perovskite. If I just double the unit cell of the perovskite, it is what the double perovskites. I am leaving this structure because of the shortage of the time. So the first thing is, in any of the material, whenever we are designing it computationally, we need to check the stability of the perovskite, and that is done with the help of the first thing is charge neutrality should be there, and there are certain well-defined tolerance at the and the octahedral factors which we need to calculate. This is the vast range of the application of the perovskites. They can be used in photovoltaic, LEDs, catalysis, energy storage, sensors, and the thermoelectric. Now coming to the methodology that I am using is, that is the density functional theory. It is a widely used and well acceptable theoretical method for the prediction of the various property of variety of material. It was started somewhere in 1927 when the Thomas Fermi model was given, where it was considered that the total energy is the function of the electron density. However, the material, this scheme or the model was very crude and it was not able to explain the large application of the materials. Then came is the Hartree-Fock method in 1930 HF, where it was considered that each and every electron in the each and every atom and the molecule is moving in the presence of a field of remaining all the electrons. So it has a drawback that it considers the effect of the electron itself. Then it was modified by the Fox later in 1932. Then the famous theorem were given by the Hohenberg and Kohn theorem, which is the basic or the boundary or the core heart of the current density functional theory. Then the Kohn-Sham proposed a equation that we are solving, and our aim is finally to solve that particular equation ultimately. Then the certain development has been done in order to achieve the exact exchange and correlation potential, and the continuous development is going on. But till now, we cannot say that any of the particular exchange correlation potential is sufficient or suitable for the application of all the materials and for all the properties. So this is what the Hohenberg-Kohn theorem. What they said is that the ground state energy is the unique function of electron density, and if I can find out the exact electron density, that will be the minimum energy of the system will be there. It means my system will be stable when I am able to predict exact electron ground state density of the material. So what we do is, in the density functional theory, we start with the initial guess of the density of the system. Then we calculate the different parameters and we check for the self consistency. If the result is same as what we propose, then we go for the further thing. We calculate the energy there. We try to obtain the minimum energy. If result is not same, we again start with the initial guess of the electron density. So here you can observe some equation. E is written as certain terms. So in summary, if I want to say, in a particular material, what we can have is, we can have the kinetic energy of the nucleus, kinetic energy of the electron interaction, nucleus interaction, and the electron nucleus interaction. The nucleus kinetic energy and the nucleus interactions are always ignored in the density functional theory, because it is assumed that if a nucleus is changing, so automatically the electron has to change their position and their energy and extra thing. So the only problem is the interaction between the electron is not known to us. So we need to provide a guess for the exchange and correlation potential. That is what the heart of the density functional theory. Okay. So this is what I will be skipping it. This is what, if I am moving towards the simplicity, I won't be getting the accuracy. If I am going for the accuracy, it will not be simple. This problem will be complex and it will be needing the high computational cost. In density functional theory, certain codes are there, softwares are there. I am using the V2K and nanodical. For some application, I am using the VASP also. So what I will be doing is, I will be summarizing certain highlight of my research work. This is what some of my students are working on the oxide-based perovskite, some are working on the halide-based perovskite, and some other one or two students are working on the chalcogen materials also. So this is what the A2ZR TiO6 perovskites. I am directly coming to the result. So as I mentioned that if we are proposing a new material or we are talking about a new material, we need to check the stability. It is not like some people think that if you are doing the theory, you are free to do anything. You can put anything in the A, you can put anything at the B side. This is not the case. You need to check for the certain thing. So initially we check it for the structural stability. For that we have calculated certain parameters. There is a well defined limit of the parameters. If my material is in cubic phase, it will be having a particular range for those parameters. If it is hexagonal, that range will be different. So we have checked the structural stability and we found that all four perovskites are the tetragonal in nature. Then again, whether we are mixing the material, we need to check the formation energy, whether it is thermodynamically possible to make the material or not. Then we have calculated the formation enthalpy also, and we obtain it as negative value. You can see it is minus 3.42 to minus 4.15 for all the material, which confirm that we can synthesize these material and they will be thermodynamically stable. Then we check whether the material will be suitable. When we are proposing it for the practical application, we need to check whether it will be able to sustain or survive if we are applying certain kind of the stress to that, or deformation is there, or some pressure is applied or not. For that we have calculated certain mechanical parameter of these material, and we found that the young modulus, bulk modulus, shear modulus, which define the different kind of the deformations and the anisotropy, and whether the material will be ductile or brittle. If it is not, if it is brittle, it won't be able for the practical application. So that we have calculated for all, and you can see that all the compounds are having the good value of all the modulus, whereas this B by G ratio, which defines whether the material will be ductile or the brittle, if it is greater than 1.75, the material will be ductile. Otherwise it will be brittle. So what we found is that our Mg and Ca based oxides are ductile in nature, whereas the Sr and Ba based compounds were brittle in nature. Then we try to find out what is the electronic property of the material, whether they are suitable for UV application or the visible application, etc. So we have calculated the energy band and density of states of the compound. We found that the band gap of these compounds were within the range of 3 eV approximately. We have checked it with the available data also. Then what is the practical application of these material? For that we have checked the optical properties of the material. So this is what the real component of the dielectric tensor, which measures the polarization and the dispersion of the interaction of photon within the material. It means if I am incidenting the light on the material, how much it will be polarized, how much it will be interacting with the material, that we have calculated. Similarly, here it shows the imaginary component of epsilon. It shows how the light will be attenuated when it is traveling through the material, that we have checked here with. Then if I am incidenting a light on a material, it can be absorbed, it can be reflected, it can be transmitted. So we checked whether it is absorbed or not. Until unless the light will not be absorbed by the material, it cannot go for any of the practical application. So we found that these compounds are showing the good absorption for the UV range, that is greater than 3 eV or 4 eV. So these compounds can be used for the UV sensors, UV detectors, etc. Reflectivity, if I am forming a material, light should enter inside it, it should be absorbed, it should not be reflected. So we find that the reflectivity of these material is very, very less. Then loss, if we are incidenting some light, how much amount of the light will be lost inside the material, that we have checked. For practical application, obviously this factor should be as small as possible. Then to check the thermoelectric application of these material, we have calculated certain parameters. Seebeck coefficient, which measures if I am changing the temperature, how much voltage will be generated. What is the electrical conductivity? What is the thermal conductivity? Then there is a parameter term as the figure of Merritt that we have calculated. So for the practical application, what should be there? The Seebeck coefficient value should be greater than 200 microvolt per Kelvin. It means if I am changing the temperature by 1 Kelvin, what is the value of this Seebeck coefficient? How much voltage will be generated? So for all the studied compound, it was in the acceptable region, and at room temperature, it was greater than 200 microvolt per Kelvin. Then the electrical conductivity, I think the lines has been some something went wrong with the PPTs. So it was up to 0 to uh, that particular value. So electrical conductivity, whether the material will be suitable for the conduction or not, whether it will allow the light to go through it or not, that we have checked, and we found that all the materials that we have calculated or we have computed, they all are having the good electrical conductivity at the room temperature. Similarly, this thermal conductivity for the practical application, it should be as small as possible. We were obtaining the same result for this, and same with the figure of merit, etc. Then this is what the summary table for the thermoelectric parameter of the all the compound, and we found that these materials are suitable for the thermoelectric application also. Then what we have done is we have applied the pressure on these material from some 0 to 45 GPa. And if we are applying the pressure on the material, whether these materials are changing their properties or not, that we have also explored. And we found that all the materials, the energy gap was increasing, and they all were stable. If we apply the pressure also, they all were showing the good absorption in the UV range. They all were having the mechanical stability based on their mechanical parameters that we have calculated. So this data is written here. I am skipping it because of the shortage of the time. You can check it in the published paper. Then we have checked it. This is what the another work. Here what we have checked is, along with the electronic, optical, mechanical property, we have checked it for the photocatalytic activity also. So we started with the initial structure. Structural optimization was done, mechanical properties were done, electronic, optical properties were calculated, and we found that these oxide-based perovskites, they are good for the UV application. I'm just coming to the additional thing that we have done here is, we checked it for the splitting of the water, whether our compounds can split the water, they can be used for the photocatalytic activity or not. So here what we obtain is, for the photocatalytic activity, the valence band is, edge and the conduction band edge, they should be in such a way that valence band edge should be below to the oxidation potential of the O2, and conduction band should be above to the reduction potential of the hydrogen. And in our case, it was observed for all the compound. What we found is, the reduction potential and the oxidation potential, they all were having the value which is above the acceptable value of the compound. So in this particular paper, we found that our materials are suitable for the photocatalytic application also. Then we checked for the effective mass and the efficiency of the separation of the electron and hole, because if I am incidenting some light, electron hole pair will be generated. If they will recombine again, if they won't be able to travel the large distance, it will be wasted. They won't be doing any kind of the application. So if I want them to split my water, they should travel a large distance. So we check their effective mass and we check their this D value, and it was quite large or higher than the required value. So here we have checked this. So I am just skipping the remaining thing. As I mentioned, some of my students are working on the halide based perovskite also. Whatever halide based perovskite we have studied, oxide based perovskites, they are having the application in the UV range. They are good for the UV sensors, detectors, etc. Whereas the halide based perovskite that we have used, they are having the large absorption in the visible range. So they are more suitable for the photovoltaic or the solar applications. So here we have discussed this. I am skipping all this, just highlighting the work. This is what again we have checked the recent published paper in Journal of Molecular Graphic and Modeling. So in nutshell, what we are doing is we are checking the basic property of the different kind of the halide and the oxide based perovskite. And what we are finding is that these materials are promising material for different electronic applications, optoelectronic applications in visible range as well as in the UV range, and they are suitable for the photocatalytic activity, thermoelectric application also. So if we are having the solar energy, we can convert it into the electrical energy. If we are having some change or the heat energy is there, so these materials can convert them into the electrical energy because they are showing the good thermoelectric properties also. So I will be stopping here because of the shortage of the time. So thank you for inviting me, and congratulate to the organizer for the event. Thank you, ma'am. Thank you so much, ma'am. Generally जो PBI3 types के होते हैं, they are best known for the solar cell. Yeah, that's what we want to replace it. That's what actually. Yeah, ma'am. I actually in my double perovskite is a much known topic for my PhD. I worked on double perovskite, especially RB2 PDF6. I have published that paper. Datta sir, want to ask question? Yashika?
We are not working, we are not looking for that. But what my MSc student has complete idea, what he is doing is, he is thinking of we are using lithium ion batteries. Okay, because we use it long back. What he is thinking is he tries to replace lithium with lithium. So right now he is looking for the different material for the node and focus. Usually we are not. Okay, apart from this, what temperature at we can use that? What maximum temperature we can and how? Maximum temperature. We were checking typically for the 800 or something like that. Up to there is probability of
Okay, I will request our HOI, Professor Seema Pathak, to felicitate Dr. Jagriti. Yeah, Yashika. So this one is our last session. After this, tomorrow again at same 9:30, we will start our second session. So if you want to close, you can close this one. Huh.
आपको जब भी हमने याद किया है आपने ऑलवेज अवेलेबल किया है ज्ञान से भी बट मैं सोचती हूँ कि पहले फिर में काम किया जा रहा लोगों के साथ आप लोग बहुत सारे और नाम सबने किया और